In this video, we'll learn how to apply some of the calculus concepts we've come across to parametric functions. And just as a reminder, a parametric function is a function in which the x and y coordinate are expressed separately as functions of a parameter, in this case time, but we'll see that that can be also another, it doesn't have to be time, it can be a different type of parameter. So the things we'd be interested in, of course, would be derivatives, and the thing to keep in mind is there are three derivatives we're probably going to be interested in this section. One of them is dy dt, one of them is dy dx, and one of them is dx dt. And they all mean different things. So I'll point those out as we're going through this. So the first thing we might want is dy dx. Now dy dx still means the slope of the tangent line. Okay, the slope of the tangent line. So I'm just going to indicate that here. That means the slope of the tangent line. Right, so parametric functions can trace all different types of pictures and curves, and dy dx will still mean the slope of the tangent to the graph at that point. Dy dx is going to mean the instantaneous rate of change of the y coordinate with respect to time. All right, so it's like you can think of that more as a speed, right? What's a velocity? What's the instantaneous velocity of the y coordinate at a certain instant in time? And then, of course, dx dt would be the instantaneous rate of change of the x coordinate. With respect to time. All right, so three different rates in there. We'll be analyzing each of them individually depending on what question we're expected to answer. For now, we want to find the slope of the tangent line. A way to recover that information if we're given a function that's defined parametrically. Now, we could, of course, try to eliminate the parameter and get an equation that relates y and x directly. However, that's not always possible, and even if it is possible, it'd be nice if there's a better way to do it. And there is. So the chain rule is stated here, which relates these three derivatives, and you can see that the chain rule is well stated here. Now if we just solve for dy dx by dividing both sides by dx dt, you've got a nice, easy to remember formula to get dy dx. Now of course this is only true if dx dt is not equal to 0, because if it's equal to 0, then what you have is a 0 in the denominator of this expression. If you think about what that means too, if dx dt is ever 0, that means that your x-coordinate of the curve was not moving at a certain instant, or was paused for an instant. And if the y-coordinate was moving, then that should create a vertical tangent. So that it makes sense that this would happen, but in any case, we wouldn't want to zero in the denominator. But there's an easy to remember formula for dy dx in terms of dy dt and dx dt. Now the second derivative we can get as well. So the second derivative would tell us about the concavity, or the shape of the curve at a given point. Now this is where you got to be careful, because it's easy to be confused by what this formula says. So let's just do it very thoroughly. I'm going to use this notation. Y prime is dy dx. So the second derivative is going to be the derivative of y prime. So I'm going to take the derivative of y prime. So what's that? Well, that's dy prime over dx, right? Now if you just follow the logic above, right, look very carefully above. When we wanted dy dx, it was dy dt over dx dt. if we want dy prime dx, it's going to be dy prime dt divided by dx dt. Okay, so this looks like nothing interesting is happening, but what I want to point out, and what we'll see in the next example, is that this here is equal to the derivative with respect to time of y prime, which is dy dx, over dx dt. Now, this dy dx here will be expressed in terms of t because of this expression up here. And in any case, if you simplify all this out, you get the differentials sort of to cancel, you'll notice that you're left with d squared y over dx squared. In other words, the definition of the second derivative. So this is what I would probably remember, either one of these two here. But in any case, just take note of the example we do in the next page, because I'm trying to prevent you from messing this up, because it's subtly confusing. Even though the notation here makes sense, the actual problems can be confusing. So just pay attention in the next example. Alright, so here let's find dy dx and the second derivative of y with respect to x given these two parametric equations. So let's start with dy dx. So we know that dy dx is just going to be dy dt divided by dx dt. Now dy, oops, there's a typo here. This is supposed to be a y. Sorry about that. So dy dt is going to be 2t, and dx dt is equal to 12 t squared minus 1. So that's straightforward. Now, the tricky part is getting the second derivative. This is equal to the derivative of dy dx with respect to time divided by dx dt. So dx dt we've already found, right? That's just 12t squared minus 1. This derivative here is the derivative of this whole thing. So we're going to have to use the quotient rule. So the derivative of that whole thing is going to be 12t minus 1 squared at the bottom. And in the top, 12t squared minus 1 times the derivative of the numerator, which is 2, minus the numerator times the derivative of 12t squared minus 1, which is 24t. Alright, so again, we took the derivative of that whole term, and our final answer ends up being, well, we've got a 12t squared minus 1 cubed in the bottom now, and I've got 24t squared minus 2 minus 48t squared. So that gives me a total of, in the numerator, let's see, negative 24 t squared minus 2. Alright, so just, I guess it's this orange box you really want to focus on. A little tricky getting the second derivative, but once you do a couple, it's not so bad. So let's look at just a small little application. If we want to find the tangent, and by that I think I'm going to interpret that as the tangent line, the equation, to the right-hand hyperbola branch, defined by this parametric equation, whose domain is negative pi over 2 to pi over 2. And we want to know the equation of the tangent at the point root 2 comma 1. So notice if you plug in pi over 4, when you plug pi over 4 in for t, you're going to get root 2 for the x-coordinate and 1 for the y-coordinate. And so that basically tells us we can start the equation of our tangent line as we normally do. We just got to find the derivative. So dy dx will be dy dt over dx dt. But dy dt is the derivative of tangent of t, which is secant squared, and the derivative of the derivative of secant is secant tangent. And we're evaluating this at pi over 4. So when we evaluate, we have the secant squared of pi over 4 divided by the secant of pi over 4 times the tangent of pi over 4. Now the secant of pi over 4, just a little trig review, is the reciprocal of the cosine of pi over 4, and the cosine of pi over 4 is 1 over root 2. So this is root 2 squared, which is 2. And then secant of pi over 4 at the bottom again would be root 2 times the tangent of pi over 4, which is 1. So we can simplify if we'd like, the 2 over root 2. That just becomes a root 2 in the top and a 1 at the bottom. I suppose we could have done that. We could have crossed off a secant right at the beginning if we wanted. If I had noticed that, I guess I didn't. But in any case, there's our derivative at that point. So that's the slope of the tangent line. That goes here. And now we've got an equation for the tangent line to the curve at the point root 2 comma 1.